In this video, we're going to talk about fractional exponents and how they relate to radicals. So earlier, we've talked about what an exponent is. If you have x raised to some power n, that just means we're going to multiply x times itself n times. So that makes sense when you're doing something like, okay, x to the fourth is x times x times x times x. But then as you've probably seen, if you have an exponent that's a fraction, that just doesn't make any sense. You can't multiply 9 by itself a half a time. So how do we decide what 9 to the 1/2 should be? And the logical explanation for this comes from the multiplication property of exponents. So if I took, for example, 9 to the 1/2 and I multiplied it by itself, by the multiplication property of exponents, we know we should be adding those exponents. And 9 to the 1/2 plus 9 to the 1/2 is 9 to the first, which is just 9. So then the idea is whatever we think 9 to the 1/2 should be, whatever it is, if we multiply it by itself, it has to give me 9. So if you think about it, the only number that's going to work is 3. So 9 to the 1/2, if we believe the multiplication property of exponents, that has to be equal to 3. So what does this really mean? Some of you know another way to get from 9 to 3 is to take the square root. The square root of 9 is the same as 9 to the 1/2. Okay, what if I took something to the 1/3, like 125 to the 1/3? Once again, I'll do this one more time. If I'm not sure what that is, I could think of it this way. If I multiply it by itself, not once, but 3 times, by the multiplication property of exponents, I would add these exponents, and 1/3 plus 1/3 plus 1/3 gives me 1. So 125 to the 1/3, whatever it is, if I multiply it by itself, I need to get to 125. The only number that's going to work is 5. So therefore, 125 to the 1/3 is the same as the cube root of 125. Cube root, recall, means a number times itself 3 times. That gives me 125, which in this case would be 5. Notice that for radicals, let me go back up here. When we talk about square roots, there really is an invisible 2 there. We just don't put it because square roots we use all the time, more frequently than other types of roots. But any kind of a radical that you're taking a cube root or a fourth root or a fifth root, we need to indicate what root we're taking by this little number here outside of the radical sign. Okay, so 16 to the 1/4. Hopefully, if you're following along here, you could probably think of a multiplication problem that I could make that would sort this out. If I multiply this by itself 4 times, I'm going to end up with 16 to the first. So 16 to the 1/4 is what I'm looking for, a number times itself 4 times. That equals 16, which is exactly what we mean by the fourth root of 16. So 16 to the 1/4 and the fourth root of 16 are exactly the same thing. And a number that works times itself 4 times that gives you 16 would be 2, right? Because 2 times 2 times 2 times 2 is 2 times 2 is 4, times 2 is 8, times another 2 is 16. So even though it doesn't really make sense if we think of it just like how I usually think of exponents, if I take x to the 1 over n, that is the same thing as saying the nth root of x. This is what a fractional exponent means, the nth root of x. Now, what if I wanted to raise something to not the 1/3, but maybe the 2/3 power? Like, what if I wanted 27 to the 2/3 power? If it was 27 to the 1/3, that would be the same as the cube root of 27. But this is 27 to the 2/3. So to do that, pull this paper away. the way we can figure out what 27 to 2/3 is to write, we could write it one of two ways. This is the same thing as 27 squared to the 1/3 power, because remember when we raise a power to a power, we would multiply those together, or 27 to the 1/3 and then square the answer, because that also would give me 2/3 when I multiply those exponents. So you can do it in theory either way, but now think about what would be involved here. We know now something to the 1/3 means I would take the cube root of what's inside. So this would be the cube root of 27 squared, or this way would be taking the cube root of 27 and then squaring the answer. So can you see which one would be easier to do without a calculator? Hopefully this is an easy call. To do this, you'd have to figure out what 27 squared is. That's a big number, and then take the cube root of that big number. But this is a lot easier because the cube root of 27 would just be a number times itself 3 times that equals 27. That number would be 3, and then I would square the answer to give me an answer of 9. So yes, if you work this out, this has to be 9 as well, but clearly this is easier. So whenever you're raising a number to a fraction where the numerator is not 1, it's going to be always, well, almost always easier to do it this way. In other words, you want to take the root first and then use your numerator to, in this case, square the answer. So another one, if I did 16 to the 3/4, again, I could write that as 16 cubed to the 1/4, or I could write that as 16 to the 1/4 cubed. And just like the last one, I mean, if I did it this way, I'd have to figure out what 16 cubed is and then take the 4th root of it. So it would work. It's just this is going to be easier. This is going to be easier. So this means take the 4th root of 16 and then cube the answer. 4th root of 16, we just did that on the previous page, is 2. So then 2 cubed is 8. So what do we learn now? We can come up with a more thorough formula for x to the m over n. Now I don't even need my numerator to be 1. You can do it one of two ways. It could be the same as the nth root of x to the m, or it could be the same thing as the nth root of x, and then I raise it to the m power. And as we've seen, it's a lot easier to do the power at the end because then you're taking the root of a smaller number. So this would be the one I would almost always do. Okay. So we'll practice. So now we'll go straight to the root. We'll practice this. So if I have 100 to the 3/2 using this, that means the denominator tells me I'm going to take the square root of 100, and the m would be 3, and then I'm going to cube my answer. Square root of 100 is 10. So 10 cubed is 1,000. Good time to pause the video. Try 8 to the 4/3. You can figure out what that is. Right? The 3 tells me I want to take the cube root of 8. The 4 tells me I'm going to raise my answer to the 4th power. Cube root of 8, a number times itself 3 times, that gives me 8, is 2. And 2 to the 4th is 16. What if I have something like 32 to the negative 2/5? We can't forget that a negative exponent means I should move this to the denominator to make it positive. So that becomes 1 over 32 to the positive 2/5. And then we can use what we were doing right now. This says take the 5th root of 32, and the 2 tells me to square that answer. Okay, the 5th root of 32. Well, we know we know 2 times itself 4 times is 16. So if I multiply that by another 2, that gives me 32. So since this is 5 2's multiplied together, the fifth root of 32 is 2. So this is 1 over 2 squared, 1 over 4. Okay, so one of the big points that I want you to get out of this is that fractional exponents and radicals are one and the same. So if you get stuck on one, you could always try changing it to the other form. Here we've been working with fractional exponents and changing it to radicals, but there's times when you have radicals and you're not sure what to do with it, you might try changing it to fractional exponents. For example, suppose I was doing a math problem and I ended up with the square root of 3 to the 6th power, and I wanted to simplify that. Well, to the 6th power, it's not too terrible. If I wanted to, I can multiply root 3 times itself 6 times and figure out what that is. But another way to do this is if I use a fractional exponent here, I know that the square root of 3 is really 3 to the 1/2, and I raise that to the 6th power. If we raise a power to a power, we're going to multiply these exponents. 1/2 times 6 is 3. So this is just 3 to the 3rd, which is 3 times 3 times 3 is 27. If you decided to do it this way, just to mention that, remember that the square root times itself, if you think about that, 3 to the 1/2 times 3 to the 1/2 gives me 3 to the 1 if I add those exponents. So that's just a 3. So another way to think about it is like I take those two root 3's times themselves gives me 3. These 2 times themselves give me another 3. And these 2 give me another 3. So there's 3 times 3 times 3, which is 27. But you could see, this would probably be better if this was a bigger power. What if that was root 3 to the 60th or something, right? That would be, you wouldn't want to multiply that out that many times. Or like this, the cube root of 10 to the 12th, I could multiply the cube root of 10 by itself 12 times, or I could use a fractional exponent and say that that's really 10 to the 1/3 raised to the 12th. 1/3 times 12 is 4, 10 to the 4th. Remember your powers of 10. 10 to the 1st is 10, 10 squared is 100, 10 cubed is 1,000, 10 to the 4th is 10,000. All right, here's another interesting thing to simplify. The cube root of 25 would be like saying a number times itself 3 times that equals 25. Well, there is a number, but it's not a pretty number, right? The square root of 25 is nice because 5 times 5 is 25. But if I had to think of a number that multiply 3 times that gives me 25, it's probably going to be like 2 point something, right? Because remember, 3 times 3 times 3 equals 27. So if you use something slightly less than 3 times itself 3 times, you could conceivably get 25, but it's probably going to be some kind of strange decimal. Same thing with the 6th root of 25. A number times itself 6 times that gives you 25 would, a number exists, but it's not a pretty number. But it turns out when I multiply these two ugly decimals, if I did them individually, together, I actually get a nice number. And to see what it is, I can change these radicals to fractional exponents. This is the same as 25 to the 1/3 times 25 to the 1/6. And our property of exponents, when we multiply, we should be adding those exponents. That's 25 to the 1/3 plus 1/6. We need a common denominator of 6. So I'll multiply this one top and bottom by 2. And that gives me 25 to the 2/6 plus 1/6, which is 25 to the 3/6. There's a good argument for reducing your fractions because you're going to miss it if you leave it like that. 3/6 is the same as 1/2, which we now know is the same as the square root of 25. So the answer is 5. Maybe another good opportunity to pause the video based on how we did this one. See if you can work out this one. Of course, it is division. but I bet you can do it if you change those to fractional exponents. All right, so what we should have here, if I rewrite the numerator, that's 16 to the 1/3 over 16 to the 1/12. Now, when we're dividing numbers with the same base, we're going to subtract the exponents. So that's 16 to the 1/3 minus 1/12. We need a common denominator of 12. So I'll multiply this one top and bottom by 4. And I get 16 to the 4/12 minus 1/12, which is really 16 to the 3/12, which reduces to 16 to the 1/4, which is the same as the 4th root of 16, which I think we did that one earlier. That would be 2. Other things you can do with this idea of radicals and fractional exponents being the same thing is simplify some awkward expressions. Sometimes you get weird answers, looking at these two, and I want to maybe try to reduce this to a single radical. So we'll change these to fractional exponents. So this inside right here is x, the 4th root of x. So that's the same as x to the 1/4. But we're taking the cube root of that answer. And taking the cube root of that means we'd really be raising this to the 1/3. And then ultimately, I'm taking the square root of all of this, right? This is the stuff inside. And taking the square root is like raising all of that to the 1/2. So rewriting this with fractional exponents, you get x to the 1/4 raised to the 1/3 raised to the 1/2. When we have powers to powers, we're just going to multiply those exponents. So this is the same as x to the 1, multiply those all together, and you get 24. So this is the same as the 24th root of x. You take the square root of the cube root of the 4th root of a number, you're effectively taking the 24th root of that number. Okay, this one looks a little bit different because I have 2 x's. Let's try writing this with fractional exponents. I'm going to start on the outside because ultimately this is the square root of a bunch of stuff. And the square root of a bunch of stuff is raising it to the 1/2. What am I taking the square root of from the outer square root? I'm taking the square root of x times the square root of x. But this is times, right? That's not the x root. X times the square root of x. So I have another x to the 1/2 here. That's this one, and this 1/2 is for the outer one. Now, there's a couple things you could do here. You could either distribute the 1/2 to both. You could combine these first. Remember, we're multiplying, so we would add those together. 1 plus 1/2 is like 2 halves plus 1/2. If I combine these together, that gives me x to the 3/2. And then here I'm multiplying the powers because I have a power to a power. So this is the same as x to the 3/4. Now the directions say simplify to a single radical. So then we have to go back and remember what this really means is the 4th root of x. You can either put the 3 there or we can cube the whole thing. It really doesn't matter. So I'll put both of these. You can do it that way too. It means the same thing. So either one of those would be fine. Okay, so maybe should have started with this, but since we're doing square roots and cube roots, it's probably good to review your perfect squares and your perfect cubes, maybe even perfect fourths. So most of you probably know your squares. There's a list of those. Cube roots, because 2 cubed is 8, the cube root of 8 is 2. Because 3 cubed is 27, the cube root of 27 is 3. The cube root of 64 is actually 4. So 4 times itself 3 times is 64. And I think I use this one as well. The cube root of 125 is 5, because 5 times itself 3 times is 125. 4th roots get tricky pretty quickly. Of course, the 4th root of 0 is 0. 4th root of 1 is 1. We did the 4th root of 16, and that was 2. 81, if you think about it, is 9 times 9, and each of those is 3 times 3. So 81 is the same as 3 to the 4th. And this is the other way to think about what's happening is if I take the fourth root of 3 to the fourth, it's just going to give me 3. And you can see why that's true, because taking the fourth root means I'm really raising it to the 1/4 power, and when I multiply, that just gives me 1. Okay, that's true for all of these, actually. Okay, so now when you talk about roots and negative numbers, um, there's some confusion sometimes. I'm actually going to use this over here for a moment. Let's talk about square roots. A lot of people think they get the idea, for example, like the square root of 4 could be plus or minus 2. That is not true. When we say the square root of 4, we are only saying positive 2. Square roots have to come out to be positive numbers. Now, where that misperception, I think, gets started is if you were trying to solve the equation x squared equals 4, the way we will solve the equation is there's two answers that work, right? Positive 2 squared equals 4, so does negative 2. So when we're solving the equation, what we do is we acknowledge there's going to be two answers. We take plus or minus the square root of 4, and that's how we get our answers of plus or minus 2. So if you're solving an equation, yes, you should do plus or minus if you're taking the square root. But if someone just says, what's the square root of 4? It is only positive 2, okay? The square root of a number should come out to be positive. Okay. Now, what about numbers inside the root? If I tried to take the square root of negative 4, what I'd be looking for is a number times itself 2 times that equals negative 4. Now, some of you have talked about imaginary numbers, I. If you use imaginary numbers, we could express the answer here, but we're only looking for real answers here, real answers. So the square root of negative 4 does not exist. It's not possible, okay? Not possible. Can't do it. But cube roots, you can. The cube root of negative 27 is, if I think of a number times itself, 3 times, that gives me negative 27. Negative 3 works, right? Negative 3 times negative 3 is 9, times another negative 3 is negative 27. And if you take the cube root of something cubed, you're just going to get that number. So that works. Now, what about the fourth root of negative 16? That would be a number times itself 4 times. That gives you negative 16. You can't do that, right? If you tried to do negative 2 times itself 4 times, that's actually going to give you positive 16, not negative 16. So the fourth root of negative 16 also is not possible. We'll just say it does not exist. DNE. Okay, I can put that up here. DNE. At least not for a real number, right? Not for real numbers. That does not exist. But a fifth root of negative 32 works because negative 2, if you multiply it by itself 5 times, gives you negative 32. So the fifth root of negative 32 would be negative 2. So what's the message here? You can you ever take an even root of a negative number? You can never do that, okay, unless we're using imaginary numbers. But you can always take the odd root. What I mean by an odd root is 5, 3, 7, right? You can take an odd root of a negative number, but never an even root. Okay. Now, when we start simplifying radical expressions with x in it, we have to be a little bit careful because remember, x is hiding a number and we have no idea what that number is. So you just saw me put there like the cube root of something cubed is the number. It would seem to make sense that the square root of x squared should just be x. However, let's put this to the test. Suppose x was equal to 3. Well, then what do we have here? We have the square root of 3 squared is equal to 3, right? But what if x is, suppose x was negative 3? Then what this is saying is the square root of negative 3 squared. If we believe the square root of x squared is x, what's acting like x is -3, we would be forced to say -3. But we know that's not true. -3 squared is 9, and the square root of 9, remember we can only do positive answers, is +3, not -3. So because of that, what we have, how do I get the right answer? If I took the absolute value of this, and I'll remind you, absolute value, when you apply that sign, it means you make, if the number's negative, we're going to make it positive. So now I have the correct answer. So to make sure that we're always going to make a true equation, if x is a negative number, this would not be true, right? We saw that right here. What we're going to do is put the absolute value on that. The square root of x squared is technically the absolute value of x. Okay. So then let's go with even powers here. What about the square root of x to the fourth? X to the fourth is x squared squared. And when I take the square root of something squared, that gives me the something. Now, what I want you to think about every time you simplify this is, would this be true whether x was a positive number or a negative number? Okay. So I use 3. Why don't we just do 1? Okay. If x is 1, 1 to the fourth is 1, and the square root of 1 to the fourth would be 1. And if you put 1 in there, that you get the right answer. If x was -1, -1 to the fourth is +1. The square root of +1 is 1. And if I put -1 in there, I get the right answer. Why? Because x is squared, right? Remember, the point of the absolute value is to make it positive, but this is already positive. So I do not need absolute values on this one because this is always positive. I'm going to put note absolute value not needed because x squared is always positive. And we need to be getting positive numbers out when we take a square root. Okay, there's this whole discussion here about when do you need absolute values. That's what we're getting into here. The square root of x to the 6. Well, x to the 6 is x cubed squared, and the square root of something squared is just the something, x cubed. So now let's put it to the test. Will I always get a positive answer for this? And hopefully you've already realized that that's not true, right? If x was -1, this would be positive. I could take the square root of that. The answer should be 1. But if x was -1 here, this is going to give me -1 here. -1 cubed is -1, and I cannot have a negative answer when I take the square root. So once again, absolute value would be required here to make that positive. I'll make a note here. Need absolute value to ensure a positive answer for any x. And if you want to try it again, imagine if x was -1, right? The square root of -1 to the 6th, according to this, would, if I just said it was -1 cubed, if I said it was x cubed, that would not be right. But if I take the absolute value, then it is right. That is the correct answer. Okay, what about x to the 8th? That's x to the 4th squared, gives me an answer of x to the 4th. Will I always get a positive answer, even if I put a negative answer in for x? Yes. So just like this one, I do not need absolute value. Now, the question I always get is, could I put absolute value? Does it hurt? It doesn't. It doesn't hurt, but you know, you don't, it's kind of redundant. Redundant means you don't really need that. It's already going to be positive. Square root of x to the 10th. X to the 10th is x to the 5th squared, which is x to the 5th. Do I need absolute values? Could this ever be negative? Yes, it could. If I put a negative number in there, so back to an absolute value. Okay, so you're probably starting to pick up on this, is that if I have an answer that's x to an even power, I don't really need it. This is just for square roots, by the way. So if answer is x to an even, then we don't need absolute values. But if it's to an odd power, then needed. Okay. And again, this is only for square roots, only for, and really technically fourth roots and even roots, only for square roots, because in a minute we're going to talk about odd roots. Now that said, okay, what if we don't have exactly an even, I'm sorry, a perfect square inside? So how do we handle that? X to the 11th, I could force it to be a perfect square, but then I'd deal with a fraction. But if I want to simplify this, what I would do is I would make this x to the 10th times x to the 1st, because I just saw up here that I could write x to the 10th as x to the 5th squared times x. And this, the square root of something squared, that would come out as x to the 5th. Now this is not a perfect square, so that's going to stay inside the root. I would have x to the 5th times the square root of x. Now the question is, do I need absolute value here like I did on the previous problem? And the answer is no, actually. We think about why, the answer comes to this. Why am I saying I need absolute values? I'm saying if I put a negative number in here, could this come out to be negative? Well, answer that question here. If I put a negative number in here, so for example, if x was negative 1 to the 11th is negative, and it would not make sense to take the square root of a negative number, right? So the difference here is because I'm taking the square root of x to the 11th, this must be, and I'm raising it to an odd power, x must be positive, or we couldn't take the square root of it, right? So for example, if I tried to do the square root of negative 1 to the 11th, that doesn't make any sense, right? That's square root of negative 1, which does not exist. So x had to be positive. And because x had to be positive, I don't have to worry about it. There's no absolute value here. Again, if you put it, technically fine, but you don't need it. So, okay, let's go with this one. Square root of 81, x to the 6. Now we've got multiple things in there. 81 is 9 squared. X to the 6th is x cubed squared. And what I'm going to do with the y to the 7th is break that up as y to the 6th times y. Because y to the 6th is y cubed squared as well. And I have an extra y. And so then the way it works is anything inside that squared can come out. So that's 9x cubed y cubed. And anything that's not a perfect square, like that y, has to stay inside. Now let's talk about absolute value. I know this is a little bit tricky, but it's actually good to kind of think about this as you move forward in math. Ask yourself, if x or y was negative in here, would it come out negative here? And in other words, do I need absolute value? And hopefully what you can see is yes for the x, right? If x was negative 1 here, negative 1 to the 6 would be positive, and I could take the square root of that, but it would come out negative here. So I do need it for the x, but for the same reason up here, I don't really need it for the y, because y was raised to the 7th power and I'm trying to take the square root of it, I know that y must have been positive, must be positive already. There's no way it could be negative or this wouldn't make any sense. So I don't really need absolute value though. Okay. So a little bit tricky there. We'll practice more of that in class. Now with cube roots, we don't really have an issue so much with absolute values, actually not at all, because remember, we can take the cube root of a positive or a negative number. So I'll make a note of that. With cube or any odd root, uh, um, don't worry about absolute values. absolute values because negative numbers inside are fine. Negative numbers are okay. So the bigger thing here is just now what I'm looking for to simplify this, I want to take the cube root of something cubed. So I now have to think about x to the 6 as being what cubed? It's x squared cubed. So the cube root of x squared to the third is just x squared. X to the 60th is what cubed? That is x to the 20th. So that's going to just be x to the 20th power. Now, what if it's not an even multiple of 3? Then I'm going to do the same idea I did with square roots, is I'm going to break up x to the 61st as x to the 60th times x to the first, and then think of this as x to the 20th cubed times x. This just becomes x to the 20th, and because I don't have a perfect cube there, I have to leave that inside the cube root. Okay. Yeah, kind of the same thing, but what if I have, this time I would have 2 x's left over. And this would be the cube root of x to the 20th cubed. And now I have 2 powers of x, but I got to get that. I have to have at least a third power to be able to do anything with that. And so that x squared has to stay inside. So this becomes x to the 20th times the cube root of x squared. Okay. You think you're catching on? Maybe try the next one here on your own. Pause the video. Okay, so 125 happens to be a perfect cube. For x to the 11th, what I want to think of is the closest multiple of 9 that's smaller than this number, which would be, did I say 9? Closest multiple of 3 that is closest to 11 is x to the 9th. I'm going to break this up as x to the 9th times x squared. For y to the 16th, closest multiple of 3 is y to the 15th times y. 5 cubed. X to the 9th is x cubed cubed. I've got an x squared left over. And y to the 15th is y to the 5th cubed with an extra y left over. Anybody who's a perfect cube can come out. So 5x cubed y to the 5th times the cube root of x squared y. One more here. Fourth root. Now we have a fourth root. So fourth root, we got to be careful here because of the absolute value thing. So now we're looking for perfect fourth roots. Perfect powers of 4. 16 is 2 to the 4th. X to the 7th, the closest power of 4 I can get out of that is just x to the 4th. That would leave me with x cubed. And y to the 12th is y cubed to the 4th. So the 2 can come out. X to the 4th root of x to the 4th is just x. 4th root of y cubed to the 4th is y cubed times the 4th root of x cubed. Okay, now let's think about this is an even root here. So does anybody need absolute values? If you put in a negative number for x or y, A, would this even make sense? And B, if it does make sense, would that answer make sense? Hopefully you can see that because x is raised to the 7th power, this means x must have been positive. Otherwise, I couldn't have taken the 4th root of it. So x must be positive, which means it's okay. There's no way this x could be negative anyhow, because x had to be positive there. Now, y to the 12th, I could put a negative number in for y, but if y was -1 here, for example, then this would be -1 cubed, which would be a negative, and I can't get a negative out of a 4th root. So technically, I am going to need an absolute value on the y cubed. Y could be negative, but answer should be positive because this is an even root. And so that's why we're putting the absolute value there. Okay. I don't think for things like placement tests, you're going to have to worry about this absolute value stuff, but it's stuff that comes up in calculus. And I want you to start thinking about that now. So don't get too concerned about that. But keep it in the back of your mind, though, that you need to sometimes worry about the absolute value. All right. Let me know if you have any questions or if you've seen any mistakes that I made. Thank you. I'll see you later.